session. I'm Eric Andrade. I'll be chairing this section. So the first speaker is Toninho Figueiredo from USP, and he's going to talk about influence of magnetic field on the two-photon absorption and Hyper-Rayleigh scattering of manganese, zinc, ferrite nanoparticles. So please.
Thank you. So I would like to thank Danilo for the kind invitation to come here again to speak with the theoreticians. We'll speak some real matter here. And the idea today is to tell you something about these ferrofluids, which are essentially colloidal systems where you have nanoparticles, typical dimensions of about 10 or 20 nanometers, and you can put this in a carrier fluid like water or like kerosene, depending on what you need for technological applications or even for medical aspects. So the idea here is to tell you that this type of experiments we did in the University of São Paulo, in complex fluids group, but we have many collaborators from Brazil and outside Brazil. These are some of them. And the question that we have to answer today is mainly if we have an eventual anisotropy in the electrical properties of these nanofluids, especially some bulk properties like the third order electrical susceptibility and the hyperpolarizability. This is a bulk property of the medium. This is essentially due to the particle itself. So we will compare what is the anisotropy of these electrical properties from the level of nanoparticles until the level of millimeters, which is the bulk material. As I told you, this type of material, they have a lot of technological application, medical application, and we learn a lot of basic physics also, take into account these nonlinear optical properties here. Well, as Danilo gave me about 2 hours to speak, I have 5 hours, I think. And so I will tell you what is essentially these nanoparticles, these ferrofluids, some words about nonlinear optics, two different experimental techniques that allows us to measure chi3 and beta age in these materials, essentially the susceptibility and hyperpolarizability, some conclusions and the take-home message. So that's the idea. So this is a typical TEM image of magnetic nanofluid. Here, the particles are essentially spheres. The typical dimension here, 10 nanometers, but you can have different forms. You can have flowers, you can have cubes. And this is made by the chemists. We can do that at the Institute of Physics now, but mainly this one, Kinari Parekh, is someone from India. He's a chemist that is the magician that can do this type of things. So these magnetic colloids, the typical dimensions, as I told you, 10 nanometers, and we will investigate essentially the temperature, about the room temperature, where we are higher than the block temperature. So we are in the superparamagnetic state of this material. This is important because we will try to see what happens when you put the magnetic field in contact with these fluids. So these are essentially pictures, typical dimension here, millimeters, okay? So if you put this fluid in a Patrick slab, and you put a magnetic field perpendicular to the surface of the field, you have this type of instabilities which are named Rosenzweig instabilities. So you form this kind of spikes. It's very interesting, and we show this for students, for example, when we visit the lab, and this is really a success when you see something coming up, and it's very nice. We constructed this. I would like to bring this here, but I was afraid because the ferrofluid is not so easy to carry. Well, so what happens when you take this type of system and we put a magnetic field? There are two critical fields. The first one is named here HC1, which you have here essentially the orientation of the dipole moment of the particles almost parallel to the magnetic field, the external magnetic field. If you increase the field here, between the first and the second critical field, you have the formation of lines of like necks, neck, where the magnetic moments are oriented, but the particles tend to attach one to each other. And if you increase more the magnetic field, what happens is that you form this type of bundles where the lines like this will come together. And these materials here, or this type of structure, you can see, for example, in optical microscopy. So the typical dimensions is of the order of microns here. Here is nanometers, and here microns. You can see in the microscope. Well, to investigate these nonlinear optical properties, give you some hints about this. When you take the total polarization, when you put your system in contact with an electric field, an external electric field, here is the first order susceptibility, the second order susceptibility, third order, and so on. So when you apply a high enough magnetic field, electric field to your system, you can have the possibility to find this high order susceptibilities. The second order susceptibility, in this case, where the magnetic field is isotropic medium, is by symmetry reasons equal to 0. So the first contribution, nonlinear optical contribution, is the third order susceptibility, and this is what we will measure with the technique I'll show you in a while. So what you have essentially is that the index of refraction of your material depends on the intensity of the light which is shining the material. So here is the usual linear index of refraction, but this is the nonlinear index of refraction. So when the intensity is important, this index of refraction is present and is related to this orders, the high order susceptibilities. In the case of the particle itself, we can imagine, for example, the interaction between the particle with a polarization here and the electric field, external electric field. This is basically the first order hyperpolarizability, which is typical from the particle itself. It's not a property of the bulk. So here we measure something characteristic of the particle, and with chi3 we have something characteristic of the bulk, the ensemble of particles. Well, just for theoreticians, some expressions just to make some good impression. Okay, this is the first, the polarization, first order. You have the first order susceptibility. It's essentially, you can write as a tensor here. The second order, in our case, is not important because the liquid is isotropic. So symmetry reasons, chi2 is equal to 0. And chi3 here, you have, for example, if you imagine that you have 3 orthogonal axes, when you put your particles in this orthogonal axis with x, y, and z, and you can put your fluid in this particular system of reference, you have here the polarization with it is proportional to the square of the field, which is basically the intensity of the light will shine your material. Well, one of the first parameters that we can measure as a nonlinear optical parameter is what we name the two-photon absorption, which is essentially imagine that you have a system with a ground state here, the first excited state. The difference in energy is not enough if the system absorbs just one photon. So if you put one photon of energy, the electron, which is here, will not be able to go to the first excited level there. However, if the intensity, I will give you some orders of magnitude of intensity, that is gigawatts per square centimeter, so it's a very high intensity, you can have the absorption of 2 photons, and the electron can come here from the ground state to the first excited state, absorbing these 2 photons. So the absorption is not only the linear absorption that we are used to, but we have a nonlinear optical absorption here, which is this beta, which is also related to chi3. So if we measure beta and N2, which is nonlinear index of refraction, we can have information about the two-photon absorption. And basically this parameter here, which is the cross-section for two-photon absorption. This is the energy of the photon. This is the number of observers that you have in your system. Okay. There is another possibility of absorption of photons in a material like the ferrofluids. You can have the ground state here, but you have the conduction band. But the electrons which are in the conduction band can also absorb photons here. And the fluence at the entrance, here's the laser beam, which is entered. The photons are coming here, your sample at that position, and the fluence, which is out of the sample, the transmittance, essentially has a dependence of the absorption, the two-photon absorption, or the free carrier absorption, which is a different process, but nonlinear also, because the electron here can also absorb two photons due to the high intensity of the laser, which is shining the sample. So this is a typical Z-scan result. I'll show you in a while what is the Z-scan. But imagine that when you have a high intensity of light at that position, the sample absorbs very much due to this free carrier absorption. So the amount of photons that comes here in the fluence out is smaller than what we have when you have a smaller intensity of the laser shining the sample. So this is a typical experiment, but I will show you in detail what is this. Well, if you have a medium here, which is named the Kerr medium, which has a nonlinear optical absorption, N2, remember that N is the index of refraction, N dot is the linear index, and 2 times I is the part corresponding to nonlinear effect. So imagine that you have a laser beam here, you have a lens of glass, which focus at a particular position of the z-axis. This is named z-scan because we will take a sample and we will scan, along the z direction. So when we do that, if we are far from the focus position, the intensity of the beam is lower because intensity is energy per second per square centimeter. So if the laser beam is high in diameter, you have a small intensity. When you go near the focus, the intensity increases for the same power of the laser. And if you go out of the focus, the intensity is smaller. So what we have here is the formation of a lens. It can be a thermal lens, can be an electronic lens, it can be a matter lens. It depends on the time dependence of the pulse of the laser shining the sample. So this is what happened. If you are far from the focus, you have essentially this kind of intensity reaching this region. The detector is here after the iris. So when you go near the focus, you see that you open the profile of the beam after the focus, so the intensity you are measuring in the iris is smaller, okay? If you cross now the focus, you go to that position, you are a focalization of the beam now, and you have now more light coming to this part of the iris. So this is the typical Z-scan profile of the normalized intensity measured in the detector. So this is essentially the technique that we use, and I'll show you the expressions that will fit this type of curve and will give to us N2, beta, etc. Well, in our case, as we are interested in the electronic lens, not thermal lens, not even matter lens, but electronic lens. The electrons will go from the steady state, from the ground state to the first excited state. We have a laser here which have pulses of the order, in time, of the order 200 femtoseconds. So this is important because we will take the time to put the electron in the excited level and coming back, and we will detect this photon that is coming back from the sample. Well, the wavelength of the laser is chosen as we know the gap between the excited state and the ground state. So we can tune the laser essentially to see this parameter. This is the intensity that we have at the focus. As I told you, 16 gigawatts per square centimeter is a very high, so you cannot shine for a lot of time, you can burn the sample. And remember that N2 is the nonlinear index of refraction. It is essentially related to the real part of the susceptibility, the third order susceptibility. So measuring this, we have this real part. And the beta, which is nonlinear optical absorption, is related to the imaginary part of chi3. So we are able, from this type of experiment, measure N2 and beta, so we have chi3 determined the real and imaginary part. So the laser beam with this type of pulse, which is reaching the sample is here, okay, this is the land. Don't worry about this. This is the first detector which takes the nonlinear optical refraction, and here is the detector which will take the absorption, because we take all the light that comes here, we divide in two. One of them, we take all the light to measure the absorption, and here we put the iris just to see the difference in the aperture of the laser due to the formation of the electronic lens in the sample here. And we make the scan of the sample along this direction. To measure beta, which is the hyperpolarizability, the first order hyperpolarizability, we have a different type of setup. This setup, we have a light laser here, which is red, the wavelength, this wavelength, 1064 nanometers. It will shine a sample of ferrofluid here, and you have the emission of the second harmonic. You have now green light coming from here. And this green light, this is the intensity of the second harmonic. This is the intensity of the line shining the sample. And there is an expression, I will not go to the details here, but it's possible to show that it is proportional to the square of beta. So if I am able to measure this parameter and this parameter, I know because I put this light there, we are able to make a graphic and essentially measure beta H. And what is interesting is that you can measure this in different orientation of your sample. Okay, we measure electrical properties using the magnetic field to orient the particles and orient the bulk. This is a typical experimental results of the normalized transmittance to measure in the iris, after the iris, as a function of the Z position of the sample, okay? This is the typical normalized transmittance. In the second detector, remember, we have two detectors. One goes directly along the Z position where you have the iris, just to see how the beam is deflected. But we have also some light which comes directly to a second detector to measure the fluence or the transmittance, normalize the transmittance. Okay, we have also models for this, and these models will fit basically one parameter. So each of these materials, each of these experimental curves are fitted with just one parameter. All the others, we know exactly what they are measured independently. So it's a very robust way to determine N2 and beta here. All the other parameters are known. And as I told you, we can make all these experiments in the presence of magnetic fields. So we put the sample there. We come with a laser which is non-polarized, but this polarizer will give the electric field of the light parallel to the magnetic field or perpendicular to the magnetic field. We can control this to measure the parameters in different orientations, the bulk and the single particle. Well, this is essentially the two-photon absorption. Now I'm giving you the results. As we have N2 and beta, we are able to calculate the cross-section of two-photon absorption. Here is for the spheres, ferrofluid, which are spheres, and here for the cubes. Here is the magnetic field perpendicular and parallel to the electric field of the light, here also. And you see that you have this anisotropy characteristic of the bulk material now, okay? This is the unity, Giga-Meyer is the unity of the sigma. My just important thing here is to see the anisotropy that you have if you shine the light parallel to the magnetic moment of the particle or perpendicular to the magnetic moment of the particle. Well, we can, with these numbers here, so parallel and perpendicular, we can measure basically the difference between them and the percentage that we have in terms of this anisotropy. And this percentage is about 23% and 27% for the bulk material, okay? Chi3, as I told you, we can measure in the direction of the magnetic field or perpendicular to the magnetic field. These are the numbers that we have. As we are with a uniaxial sample, when you align the sample parallel to the magnetic field, you have basically a degeneracy of the plane perpendicular to the axis where the magnetic field is placed. So what we can measure is the Chi3 along the direction of the field and the mean value in this point, in this plane. And this is what we did here. So this is what we measure along the direction of the magnetic moment of the particles, and this is the parallel. Also, we see an anisotropy, which is of the order of 70% here in beta. Here is the anisotropy of the hyperpolarizability in squares and spheres, parallel and perpendicular to the magnetic field. So you can see here that in the level of the particle, this anisotropy is much smaller than the anisotropy of the bulk. So what happens in the level of the bulk is not just a sum of the effects of each particle, but there is a correlation between them, which makes the magnetic properties of the bulk higher than that of the single particle. So what we did after is to see exactly what is happening from the nanoscale point of view. We take this material as a function of the magnetic field, when see by small angle X-ray scattering, and we saw that basically we have the formation of this type of linear structures. In the magnetic field, we analyze it to measure Chi3 and beta H. And it's interesting that the magnetic moment of the particle is aligned along the 1-1-1 direction of the crystal spinel crystal structure of the sample. So just to give you, let's see if this movie will work. Just to give you an idea what we have, you have the cubes here, the magnetic moment. If you increase the field here, what happens is that the moments will align parallel to each other. You have an increase of the size of these lines, and this we are able to see in the X-ray experiment. Well, take-home message, what we have essentially for this type of particles with different materials, essentially is a very normal condition that we have in ferrofluids. These are the parameters. The optical anisotropy, when you put an external magnetic field, appears. It's not an anisotropy which is directly related to each particle individually, but there is an effect of the sum of all the particles together that imposes the formation of this type of structures. And in the case of Chi3, this anisotropy is high. But in the case of the single particle, this anisotropy is very small. So if you take one of this, the electrical property of one particle has an anisotropy of about 70%, but when you make this type of arrangement, this can have a very higher anisotropy. This can have a lot of implications from the technological point of view. For example, if you take an optical fiber and you put this material inside, you can filter some type of frequencies, for example, increasing or decreasing the nonlinear optical absorption. So this is now used for this type of optical device. Well, so this oriented nanoparticles has this anisotropy due to the two-photon absorption. The external magnetic field makes the formation of this structures, big structures. It can be still bigger if you increase the magnetic field outside the optical fiber, for example. And for medical application, there is also some ideas. If you are interested, I can speak something about that. I think this is all. Thank you very much.
Thank you for the very nice talk. Questions?
Opa.
Okay, thank you for the talk. I have a basic question about Chi3, and it's a fourth order tensor, but I assume there are only a few components that are independent, for instance.
Yeah.
Is that the same? You apply the same kind of symmetry that you apply for fluids, for instance? You have just an isotropic fluids with like two components, or I don't know.
Yes, exactly. We take the elements of the main diagonal, and I put the main diagonal XXX in the direction of the magnetic moment. And after that, we have the two others, which is perpendicular to that one. So that's the idea.
Okay. And the second question, very quickly, are those fields the critical fields, like in phase transitions, or they are like, you have a signature for phase transition there?
No.
HC1 and HC2? Okay.
Yeah, I named it this phase transition, but really it's not a phase transition.
Okay.
I could name this, I don't know, not critical, what special fields. There's no symmetry breaking there. Yeah.
Well, so how is the dependency of the Z-scan results regarding to the nanoparticle dispersion size? Can you say something about that? Or?
Yeah, the dispersion here, if you take, for example, a typical ferrofluid, this one we have, the distribution, if you have the number of particles as a function of the diameter, you have a log normal distribution. Depending on the chemistry you do that, you can make this very narrow. So this results I show you, as I show you in the TM, is very narrow. But it certainly depends on the size of the particles. But in usual ferrofluid, the dispersion, the sigma of the log normal is about 0.3, 0.4. So it's not too much. This is still smaller. We can filter this to have a particular type of particle that is very narrow diameter. This is the experiment done.
Very, very nice results. I couldn't follow all the mathematics, but so I have two questions that might be in your equations. So you've used this manganese 0.5, zinc 0.5, iron oxide.
Yeah.
So is there a special reason for this specific material, or it should work with other materials? And the second question is, so you have more or less spherical nanoparticles. Besides the size, would shape change the properties or the equations that you use here? So how would this influence in the...
Yes, this composition, 0.5, it's very critical to define the final shape of the particle. So if you change a little bit this, you can go from flowers, they call this flowers, but it's something like petals, to squares, to spheres, to nanorods. So depending on this chemical balance, I asked already the chemists if they understand what is going on. They have some hints, but they don't have still the complete question or answer to this question. Yes. And the second one?
The shape of the...
Yeah, the shape is defined by this relation between the different components of the particles.
But if you have a cube, let's say, would the same physics, would it behave similar to what you've shown?
In terms of the magnetic field, yes. In terms of, you can change, for example, the zinc to cobalt, to manganese. You can put different types of atoms there, which will define new values for mu, for the magnetic moment of the particle, but always in the same range.
Yeah, I have a question related to the HC1 and HC2. The Chi3 data you showed were basically straight lines. It doesn't seem to have different regimes below HC1 or HC2 and so on. First of all, do you know what HC1 and HC2 is, and wouldn't you expect different regimes in your data?
Yeah. All the measurements I did here was in between HC1 and HC2. When you go to HC1 is about 100 Gauss. 1,000 Gauss. We are in 2,700. HC2 is much more than this, to form these bundles. We did not do any measurement on this because we have no control of the size of these bundles when you are in the field higher than HC2. They form, and we don't know exactly why they form different types of structures. Some of them you can see in the microscope, in the optical microscope. So you have something like microns, but certainly you have something smaller than this. You have a distribution. But we don't went to this particular age field.
And as you cross HC1, you see any change in regime?
No, the thing we did here was just between both. It's something that should be interesting to see, certainly.
Thank you.
For the questions? So if not, let's thank Toninho again. Thank you.
Thank you.